Hello friends, today we are going to discuss about stereochemistry. Our today's module will comprise of enantiomers, configuration, chiral center, reaction involving stereoisomers, stereoselective and stereospecific reactions. So I will start with introduction. Stereochemistry, as you all know, is a chemistry and its scope extends considerably beyond the static description of molecular geometry and of the physical properties related to such geometry. Means we have to discuss about the geometry of stereo molecules. Stereochemistry is concerned also with the relationship in space, of course 3D, between the different atoms and the groups in a molecule during reaction, and the way in which chemical equilibria. I hope you all know about equilibria. Equilibria means where the reaction proceeds and the rate of reaction are affected by those spatial relationships. Despite the increasing importance of the dynamic aspects of stereochemistry, dear students, it is well to start our discussion by the consideration of static molecules. Stereochemistry may be defined as the part of chemistry which deals with the three-dimensional structure of the molecule, 3D structure, and the effect on chemical behavior, their absolute configuration in space, their stereospecific and stereoselective reactions. Configuration is a term which refers to the relative position, means the position cis, trans, anti, syn, we will discuss later, but the configuration is a term which refers to the relative position or the order of the arrangement of atom in space that characterized a certain stereoisomer. The term absolute configuration refers to the actual order of arrangement of the atom about a chiral center. Already we have dealt. Chiral carbon is a carbon which is having 4 different groups attached to it. The condition for the creation of stereoisomer is the presence of at least one asymmetric carbon atom. Asymmetric carbon atom means which have no symmetry, or the other 4 binding atom in a molecule. Static stereochemistry, perhaps better called stereochemistry of molecules, which deals with the counting of stereoisomers with their structures, that of course is molecular architecture, with their energy and with their physical and most of their spectral properties. Whereas dynamic stereochemistry or the stereochemistry of reactions, means where the reactions will be entertained, deals with the stereochemical requirement and the stereochemical outcome of the reaction, including interconversion of conformational isomers or topomers. I hope we will have a very exhausting as well as interesting topics ahead. So please be listen attentively. Thank you. Module 2, that is of course enantiomers. Enantiomer stereoisomerism can be broadly classified into 2 classes. First and foremost is configurational isomerism, that comprises of stereoisomers which are non-superimposable and non-interconvertible by rotation around the single bonds, known as configurational isomers, and the phenomena known as configurational isomerism. The configurational isomers can be interconvert only by making or breaking, means we have to either make the bond or break the bond. These isomers further may be 2 types. First is enantiomers, that is also known as optical isomer, because they have the optical activity. When the 2 isomers are mirror image of each other, they are known as enantiomers. This is also known as inversional isomerism, means mirror image. Diastereomers, when the configurational isomers are mirror image of each other, these are known as diastereomers. Also includes geometrical isomers. So major difference I would say is optical isomers and geometrical isomers in enantiomers and diastereomers. Enantiomers is optical isomers, whereas diastereomers is geometrical isomers. Okay, I hope you all got this. Next is conformational isomerism. These stereoisomers which are non-superimposable but easily interconvertible by the rotation of bonds with the carbon atoms about single bonds, conformational isomers or known as conformers. Students, please be attentive because there are newer terms will comes to you, so please be attentive. I would like to introduce a broader classification of all the isomerism, stereoisomerism specifically. Now dear students, look, isomers, first is constitutional isomers, different carbon connectivities, different atom connectivities I would say, and then stereoisomers, same atom connectivity, different arrangement in space. The absolute thing what we had to learn in stereochemistry is the arrangement of atom in 3D. Then stereoisomers that has been further classified in two of the things. First is configurational, means separable, conformational, related by rotation around a single bond, where configurational is further classified in enantiomers and diastereomers. Enantiomers are non-superimposable mirror image, where diastereomers are stereoisomers that are not mirror image. Okay, now we will further proceed to our topic. So the different types of isomers, a carbon atom that is to bonded with 4 different atoms groups loses all symmetry. When a carbon atom is attached to 4 different atoms, means it loses all of its symmetry. How many valencies is carbon having? Anyone of you know? Carbon is having valency of 4 because 1, 2, 3 and 4, and it is often referred to as an asymmetric carbon. A carbon which is having 4 different group attached is known as asymmetric carbon. The configuration of such molecular unit is known as chiral, and the structure may exist in either a right-handed configuration or left-handed configuration, one the mirror image of each other. This type of configurational stereoisomerism is termed as enantiomorphism. And the non-identical mirror image pair of stereoisomer that results are called enantiomers. Enantiomers have identical physical and chemical properties. I would say physiochemical properties like melting points, boiling point, density, refractive indices, etc. They differ only in their action on the action of their plane polarized light. One of the enantiomer rotates the plane polarized towards the right and the other one to the left. Enantiomers shows different properties, physical or chemical, only in a chiral medium. Polarized light provides such a medium, and in it enantiomers differs in physical properties of the rotation of light, which we all know. They may also differ in solubility and in an optically active solvent or in adsorption. I know you know the difference between the absorption and adsorption. I hope you know. Adsorption always refers to the surface only, or in the adsorption on an optically active surface. For an enantiomer to react at different rate, the necessary chiral medium can be provided in a number of ways: by an optically active reagent, or by a chiral solvent, or by a chiral surface of a catalyst. Dear students, we will discuss here with the properties of enantiomers, how enantiomer behaves. Enantiomer shows similarity in most of their physical properties like melting point, boiling point, refractive index, etc. These properties are dependent on the intermolecular forces. Again, the new term come, intermolecular forces in between two molecules, that known as intermolecular forces working between the molecules. The mirror image forms have the same type of intermolecular forces working between the molecules. As a result, they show similarity in physical property. However, the difference in the property of the two enantiomeric forms observed in two different ways. What it can be? First is reactivity of the enantiomers with other optically active chiral molecules, and another one, the deflection of the plane polarized lights. Reactivity of the enantiomers with the other optically active compound is the reactivity of the optically active enantiomeric form of the molecule with another optically active compound differs. Optically active enantiomeric forms of a molecule react with the same rate with an optically inactive compound. Optically active enantiomeric forms of a molecule shows difference in a rate on reacting with one of the enantiomeric forms of another optically active chiral compound. Please be attentive because you will be getting confused, but don't need to get confused, be attentive. The difference in between the rate of reaction is observed as the two transition state and the product obtained by the reaction of enantiomers of the optically active reagent are not mirror image forms of each other. Since the transitional state obtained, I hope you all know about the transition state, a state where one molecule is about to transform to other state, that is known as transitional state. Since the transitional state obtained during the course of reaction are different, the energy contained possessed by transitional state would also be different, obviously, and therefore the rate of reaction would also differ. Means rate of reaction is always associated with the energy of the molecule have. Dear student, how you are feeling now? Now we will start our module 3, that of course is configurations. How many of you know about configuration? Configuration has been defined by Cross and Klein in way back 1976, IUPAC 1979, as the arrangement of the atom in space of the molecule of defined constitution without regard to arrangement that differ only as after rotation about one or more single bonds. Do you know the difference in between single, double and triple bonds? I know, I hope you know. The unsaturation. The unsaturation means if the unsaturation is there, there will be double bonds. But we are here only discussing about single bond. By the term configuration, we mean the arrangement of atom groups around the asymmetric center. Asymmetric center means a center which has no symmetry, which is the most commonly carbon or nitrogen. This is generally observed in carbon atom and in nitrogen atom because they have the valency of 4 and 3. It must be very clear to reader that there is no significant relation between the sign of rotation and the configuration of enantiomer because the compound and its derivative having same configuration may have a different sign of rotation. Maybe it may be levo or it may be dextro. Likewise, it has been observed in lactic acid and its ester. Although the configuration is same but possess opposite sign of rotation, it has been visualized that plus 3.820 and minus 8.250 respectively in the lactic acid. The determination and specification of configuration is essential part of the structure determination of molecule. Of course, this is helpful in determining the structure. Here is one application comes to you of stereochemistry, that is the determination of structure. Okay, determination of molecule displaying the stereoisomerism including chiral ones the relative configuration. Now we will know about relative configuration, D and L nomenclature. Way back 1951, there was no method for determining the absolute configuration of a compound, and hence the configuration of all the compounds were studied with respect to glyceraldehyde. Means there is a standard glyceraldehyde we had taken as a standard, and we are taking the configuration against to glyceraldehyde. This is way back 1951. Now the relative configuration, Rosenhoff chose glyceraldehyde as arbitrary standard because of the relationship with carbohydrates, plus glyceraldehydes having OH group on the right and the mirror image of compound, of course, minus glyceraldehyde, in which the OH group is on left. The D and L nomenclature of configuration can also extend it to compounds possessing more than one asymmetric carbon atoms and to the compounds having asymmetric carbon atoms in rings. Means we are here going to discuss about cyclic product also. Absolute configuration, R and S nomenclature. You have gone through with the D and L nomenclature, where we had taken the standard of glyceraldehyde, the position of hydroxy group. Now again a type of configuration that indicates the absolute configuration, where the prefix will be used as R and S. I hope we have a image previously where I had given you the enantiomer image. It has the prefix of R and S. Now the term R and S will be very much clear to you. So absolute configuration, R and S nomenclature. R and S assignment to distinguish between the two enantiomers. One is called S enantiomers and other is called R enantiomers. The R and S assignments are designated by a Kohn-Ingold Prelog convention. It is known as also CIP. Each chiral center is designated either R or S. Means we have prefix added to only to chiral center. Okay. There are two steps to assigning R and S as an enantiomer. The first one is assignment of priority. How many of you know about the meaning of priority? Means what we have to take in first. Okay. Assignment of priority to the groups bound to the asymmetric carbon. Now we will look at the atom directly bound to the chiral carbon. The first step is atoms with higher atomic number receive the higher priority. Means our first priority is to take an higher atomic number. Means iodine is having higher molecular weight as compared to sulfur, or higher atomic number as compared to sulfur, then oxygen, then nitrogen, then carbon in isotopic form, 13 C13, C12, again lithium, then again the three isotopes of hydrogen, deuterium and tritium. Okay, now this is the way we have to set our priorities. Then other step is, in the case of the same atom being bounded directly to chiral carbon, we go to the next atom along the chain. Means if the same atom is bounded to the chain, means either bromine, either chlorine, then we have to move with the chain. Likewise CH2Br, CHCl2, CH3 thrice, CH, CH3, CH2F, CH, CH3 twice, CH2, CH3, likewise only. That once you have know this, the priority, you have set your, first and foremost, you set your priority list, then nomenclature. Okay. Now the third point is double and triple bonds are treated as if each bonds were as a separate atom. Imagine that each pi bond is broken and the atoms at the both ends were duplicated. Now the second part of this R and S assignment is, first the molecule is drawn is three-dimensional and arranged in such a way that the bond between the chiral carbon and the lowest priority groups heads back into the paper. First we have to set the priority, then lowest priority. B. Draw an arrow from the groups of the highest priority. There we have to draw an arrow from the highest priority. First we have to take highest priority, then the least priority, to the second and to the third priority group. If the arrow is clockwise, now you are getting my point. First we have to set our priority, then we have to put an arrow. If the arrow is clockwise, the chiral carbon is assigned as R. If the arrow is counterclockwise, the carbon is assigned as S. I hope you are clear now. Okay, this is all about R and S nomenclature. So in this module what we have dealt, the DNL nomenclature, and then we have R and S nomenclature. R and S nomenclature has been given to us by CIP, that also known as CIP system. Okay. Dear students, how are you feeling now? Okay, now we will start our chiral center. There are so many new terms comes in your way now. Chiral center, every object has a mirror image, but if a molecule's mirror image is different from the other molecule, it is said to be chiral molecule. Chiral objects includes our hands, means these palms, these are two chirals. Our feet, globes, screws, corkscrews. I hope you have seen all these things in your day-to-day life. I hope you do. A chiral objects have mirror image that are identical to the object. In 1964, Kahn, Ingold and Prelog proposed that chemists use the terms chiral. Chirality as defined by Kelvin. The chirality means handedness. The based on the Greek word for hand is chair, in reference to that pair of non-superimposable mirror image. Chirality in organic molecules, it has been already observed in organic molecules. If a mirror image of a molecule can be placed on the top of original and the three-dimensional arrangement of every atom is the same, then the two molecules are superimposable. They are superimposable to each other, and the molecules is a chiral. If a molecule has non-superimposable mirror image, it is chiral. A compound whose molecules are chiral can exist as enantiomers. Compound whose molecules are achiral can also exist as enantiomers, means for the property of enantiomer they don't need to be chiral. Now chiral center, a carbon atom to which 4 different groups are attached is a chiral center, sometimes called chiral carbon also, because carbon is having the valency of 4, we already know this. Many but not at all molecules that contain a chiral center are chiral. Many but not all chiral molecules contain a chiral center. Possibilities are there because exceptions is always. Another example of stereoisomers of 2-chlorobutene A and B, stereoisomers carbon are stereocenters. A and B are superimposable mirror image. Now we will start our module 5. Module 5, reaction involving stereoisomers. Stereochemistry plays a very important role in number of reactions and their mechanism, means there are number of reactions which has been having the importance of stereoisomers. Many reactions have been found to be stereo-specific and stereo-selective. So first we know stereo-specific and stereo-selective. Stereo-specific reactions are those reactions in which a stereoisomeric form of the molecule reacts in a manner to gives only a specific stereoisomeric form of the product. Please be attentive, a reaction which will give a stereoisomeric form of the product. For example, bromine added to cis-butene to give exclusively an optically active product. Stereoselective reaction. Stereoselective reactions are reactions in which the reactant produces predominantly or exclusively one of the stereoisomeric form of the product out of the all stereoisomeric forms that are possible, means there will be only one product. Okay, you have got the difference. It will be having the product stereospecific. Stereoselective will produce only one specific product. For example, dehydrogenation of reaction preferably gives the trans alkene product. Now we will discuss various types of reactions of stereoselective and stereospecific one. The reaction involving inversion, retention and racemization. Do you know the inversion, retention and racemization? Inversion means configuration D becomes to L or L becomes to D. Retention, if it is D, it becomes D only. If it is L, it retained to L only. And racemization means racemization of both the forms. Stereoisomers can undergo reaction involving either inversion of configuration or retention of configuration, or maybe result of giving in giving a racemized product, means it can be invert product or it may be the same what it was in the initial state. Reaction involving racemization. Unimolecular nucleophilic substitution reactions occurs through the formation of a carbocation, a chiral molecule. Carbocation is always having the charge positive one. Okay. For example, 3-bromo-3-methyl hexene when subjected to solvolysis reaction undergoes unimolecular nucleophilic substitution reaction through the formation of an achiral carbocation, a carbocation positive charge, as intermediate. The achiral intermediate in turn gives equal quantities of both the enantiomeric forms or a racemic forms or a racemic mixture as product. Now the another reaction involving inversion of configuration, means configuration will be invert. Inversion of configuration of an optically active compound can be observed when a molecule undergoes bimolecular nucleophilic substitution reactions. Now the third reaction involving retention of configuration, means where there will be no change. Okay, retention of configuration of a chiral molecule would occur in a nucleophilic substitution reaction. The attacking group links to the chiral carbon atom from the same side which the leaving group is attached, means if the leaving group is attached here, the molecule will be attached here only. The existence of the stereoisomers and their involvement in chemical reaction in which stereoisomers are formed and the reaction in which stereoisomers are consumed, means a reaction one where stereoisomers are being formed and another one where the stereoisomers is being consumed, and the reaction in which the reagent is of the optically inactive or active. Few of them are the conversion of an achiral molecule into chiral molecule with the generation of a chiral center, a reaction of chiral molecule in which bonds to the chiral center are not broken, and see how such reactions can be used to relate the configuration of one compound with another. Reaction of the kind in which a second chiral center is generated, means there is one more chiral center is generated. Reaction to a compound with optically active reagents, and the examples are starting material with an achiral compound, the product will be achiral or racemic, like for the case of butane plus bromine. When butane reacted with bromine, a racemic 2-bromobutene product observed, achiral 2-butyl radical. Another example is 1-butene when reacted with acid, a racemic 1,2-epoxybutane, equal reaction top to bottom. Another example, when cyclohexane reacted with bromine, a racemic trans 1,2-dibromocyclohexane. When another example, when cis or trans 2-butene reacted with hydrogen bromide, the product will be racemic 2-bromobutane. Another example, cis 2-butene when reacted with bromine, racemic product 2,3-dibromobutene observed. Another example, when trans 2-butene reacted with bromine, meso 2,3-dibromobutane observed. A starting material with a chiral compound, you must follow the mechanism. For an example, when 3-methyl octane reacted with bromine, racemic 3-bromo 3-methyl octane observed. For an example, stereochemical changes during substitution reaction. Now we will start our module 6. Module 6, stereoselective and stereospecific reactions. Stereoisomers may react at widely different rate but yield the same stereoisomers as the product, or the yield the product that differ in ways other than in the stereochemistry. Sometimes one stereoisomer react readily and the other does not at all. Some reactions are stereospecific but not stereoselective. The quality of stereoselectivity is concerned solely with the product. I hope you mark this, solely with the product, okay, and their stereochemistry. The quality of stereospecificity is focused on the reactant and their stereochemistry. It is concerned with the product too, but only as they provides evidence of a difference in behavior between reactants. Each behaves in its own specific way. Stereoselective and stereospecific reactions. You have an example shown on your screen. A reaction that yields predominantly one stereoisomers or one pair of enantiomer of several diastereomers is called a stereoselective reaction. In this case, meso product is produced and not the other two diastereomers. Image is shown on your screen. A reaction in which stereochemically different molecules react differently is called stereospecific reaction. In this case, cis and trans stereoisomers give different product. Image is shown on your screen. The fact that the addition of halogens to alkenes is both stereoselective and stereospecific gives us an additional information about the stereochemistry of the addition and the mechanism for the reactions. Now the image which is showing on your screen giving you an impression that there are two types of additions possible. Two types of additions are possible. First is from syn, another from is anti. Syn means same side, anti means different side. Okay, thank you. Dear students, now we will conclude our topic, a part of stereochemistry which deals with the three-dimensional structure of the molecule and its effects on chemical behavior. Chemical behavior, now it is already clear to you, like physiochemical properties, rate of reactions, reaction equilibria and all those. Their absolute configuration in space means their arrangement in space. Their stereospecific and stereoselective reactions means either a product or a specific product may be defined as stereochemistry. Absolute configuration refers to the actual order of the arrangement of atom about a chiral center. The physiochemical properties of an enantiomers are identical except for the sign of rotation of plane of polarized light D or L, dextro or levo. A racemate is a mixture of both the enantiomers in equal proportions. Stereochemistry plays a vital role in our day-to-day life. It has been observed that many of the living systems, plants and many pharmaceutical processes or respond to only a particular type of arrangement. Arrangement means again a form, dextro or levo in a molecule, and are found to be stereospecific in nature. For example, the double helical form of DNA turns in a right-handed way. Honeysuckle vines as a left-handed helix. Only one form of sugar plays a unique role in animal metabolism and is become the basis of their multi-million-dollar fermentation industry. Similarly, only one isomeric form of chloromazetine acts as an antibiotic. Among amino acids, it has been found that only one form of asparagine and one leucine are sweet, and only one of the glutamic acid enhances the flavor of food. Thus, stereochemistry and stereospecificity becomes a very important part of our life. Thank you so much.